All right, so before we get started on talking about the topics of linear algebra, there's some preliminary things that are worth covering here. Technically, most of this stuff should have been covered in prerequisite courses that you may have taken, but some of the notation that we're going to cover here may not be familiar to you, and we're going to be using it a lot in this course. So I wanted to spend some time to go over that now before we start jumping into the first chapter of our book. So the first thing I want to talk about is sets. When you study math, starting in about algebra, you start introducing the concept of sets. You talk about solution sets for, equations, polynomial equations. For example, a quadratic might have two solutions, and you can talk about its solution set as the set containing the two numbers that are the solutions to that quadratic equation. But sets come in all different varieties. Intervals of real numbers are sets. They have an infinite number of numbers in them, typically. But the actual definition of a set is actually much more general than that. A set is defined to be any collection of objects, and that's very vague, and that's intentional because we want the definition of a set to be general enough to allow us to do lots of different things with this idea. Individual objects that are contained in a set are called elements. And here we're going to talk about three different ways of describing describing a set. So English description, this is the simplest and most straightforward way, but it's also the one that we use the least. And simply a literal description in words of what the set in question is. So we could talk about the set of solutions to this equation, for example. Or we could talk about the set of single variable functions that are differentiable on the interval 0, 1. That's an infinite set. There's an infinite number of functions that are differentiable on this interval. We could talk about the set of giraffes named Hank living in my backyard. That's meant to be kind of a ridiculous one, but it's something that technically could be described as a set. Just in case you were wondering, I don't have any giraffes in my backyard, much less a giraffe named Hank. So this is a kind of a silly example, but it also illustrates something important, something that we call the empty set, which we'll talk about in a little bit. Because there are no giraffes in my backyard named Hank, this set contains nothing. We call it the empty set. Another common notation for sets is listing or roster notation, which is what it sounds like. We're listing the elements of a set. Now you'll notice this first set, 1, 2, 3, ... This indicates that this is an infinite set, and that ... indicates a pattern in this sequence of numbers here. So this would be all of the positive integers, 1, 2, 3, and so on. Here's a finite set containing three functions, sine of x, cosine of x, e to the x. It's important to understand that sets don't need to contain numbers. That's why our definition of a set said objects, not necessarily numbers. Most of the sets you've dealt with up until this point have probably only consisted of numbers, but we're going to be dealing with sets of functions a lot as well as sets of vectors, sets of matrices, sets of all kinds of different things. Here's another example of a set. It's a set of monomials, x squared, x cubed. You can see that there's a pattern in the exponents here, and this indicates that pattern it goes on forever, and so this is another infinite set. Finally, we use this notation a lot, and this is the one that takes the most getting used to, but you should have seen this before as well. It's called set builder notation. And in set builder notation, you see these curly brackets just the same way that we do in listing or roster notation, but the format is different. You see this little vertical bar here. When you see that vertical bar, you read that as such that. So, for example, this first set I would read as the set of all x such that x squared is greater than 1. This here indicates what the elements look like. So these look like single real numbers, and then, let me just say real numbers. They look like real numbers, and then this indicates a property that all of the elements of this set must satisfy. More specifically, the set will contain all of the numbers that satisfy this property. That's actually a little bit different than what I just said. Here's another set. This set we can see contains ordered pairs. So this this thing that's being shown to the left of that bar is, again, indicating what types of objects are in this set. Real numbers here, ordered pairs of real numbers here. And it says that this is the set of all ordered pairs of real numbers x and y, such that x squared plus y squared equals 1. Now, this set is the unit circle. This is a way of describing the unit circle from trigonometry. It's just given in a different notation. Here, this is the set of all differentiable functions. We could read this as the set of all functions f of x such that f is differentiable. And remember, when we say differentiable, we mean differentiable on the whole real line. That's what that implies. So different ways of representing sets. These are all important to be familiar with. Moving down a little bit, we talked about this before. The set containing no elements is what we call the empty set, or the null set. You sometimes see it called that as well. And we typically notate it with this circle with a line through it, or with curly brackets, but nothing between them. When you're first learning about sets, and you start learning about the empty set, it may seem kind of weird that we would even need to talk about a set that contains nothing. It turns out the empty set is actually one of the most useful sets to have a definition for. But because this isn't a course on set theory, we can't go into too much of that. You're just going to have to take my word for it. It's actually incredibly useful to have this empty set. We'll actually see it show up in a definition that comes up a little bit later. Moving on. We're going to use a symbol here. This is a Greek epsilon. It says if A is a set containing the element x, we use this notation to describe that. X is an element of A. That's how you read that, is an element of. You may have seen this notation before. Your book, for reasons I'm not quite sure of, doesn't really use set notation very much. I don't know why. It makes everything that we do in this class much easier and much more efficient if we use this notation. So I'm going to use it in my lectures. Your book avoids this for the most part for some reason. This is just to get you familiar with it when you see it in my lectures. If we want to indicate that x is not an element of a particular set A, then we can write this notation, that element notation with a line through it. So this says x is not an element of A. Okay. Now, there are certain sets that we're going to be using over and over and over again, and because they're so common, we give them special symbols. So, for example, this is this R here, this capital R represents the set of all real numbers. You notice it's not just a capital R, it has kind of a thick notation. This is usually called Blackboard Bold. That's the name for that kind of font. But that's going to represent the set of real numbers, all real numbers. We also are going to be commonly or very frequently talking about sets of ordered n tuples. If n is 2, then we're talking about ordered pairs. If n is 3, we're talking about ordered triples. Ordered n tuples is the general term for an ordered set of n real numbers. So x1, x2, all the way through xn, and the order here matters, hence the name ordered. So this in set builder notation is a description of the set of all ordered n tuples of real numbers. You should see the property here that this is supposed to satisfy. Our notation for the set of all ordered n tuples is Rn. The n looks like an exponent here. And if n is equal to 1, we think of that as the same thing as just R, the set of real numbers. Okay, so this notation is something that we're going to be using throughout the entirety of this course. Very important to understand what that means. All right, a little bit more on sets. So if we're comparing two sets, if you have a set B, and if you know that every element of the set B is also contained in another set A, then we can say that B is a subset of A, and we use this notation. It looks like a little sideways capital U with a line under it. The line down here is intended to be used in a similar way as when you say, this number is less than or equal to another number. That little line can be thought of as or equal to. And what that means is that B may contain all of the same elements of A, but not only that, they may in fact be the exact same set, which means A doesn't contain anything more than B does. So if a set is equal to another set, we can also say that it's a subset. It still fits the definition. Okay. Sometimes, though, we want to indicate that B is, in a certain sense, a smaller subset of A. In other words, everything in B is contained in A, but A also has other elements that are not also contained in B. In those cases, we say that B is a proper subset of A, and we can get rid of that little or equal to symbol. Usually, we just write this in most cases. We don't really bother with this notation unless there's a reason for emphasizing that B is a proper subset. Okay. All right. So when it comes to subsets, there's a couple of important facts that we need to mention. First of all, every set is a subset of itself. And I say, can you see why? And I'll let you think about that. But if you go straight to the definition of a subset, you should be able to see why a set is considered a subset of itself. The second one we're going to prove. So the empty set is a subset of every set. That may seem a little bit weird because, again, the empty set is sort of a tricky thing to wrap your mind around. Why would we bother with a set that has nothing in it? And if it has nothing in it, how then could we call that a subset of some other set? Well, the proof of this, which we're going to prove here, is a proof by contradiction. And this is a really powerful proof method, and you're going to see it used at different points throughout this course. So this is a great way to kind of introduce you to a proof by contradiction. The idea behind a proof by contradiction is you assume the negation, which is in proof terms kind of the opposite of what it is you're trying to prove, and then show that that assumption leads to some kind of logical contradiction. That would imply that your original assumption was incorrect, which means the thing that you were trying to prove in the first place must be true. So here's an example. What we want to prove is that for any set, which I'm going to call some arbitrary set A, we want to assume that regardless of what the set A is, the empty set is a subset of A. So if I'm aiming for a proof by contradiction, we want to assume that that's not true. I say here, let's let A be a set, and let's assume that the empty set is not a subset of A. Now let's think about what it means for something to be a subset. And then, based on that definition, let's talk about what it would mean for something to not be a subset. So, in order for the empty set to be a subset of A, then every element of this set has to belong to this set. If this is not a subset of A, then that would imply that this set contains an element that's not in A. That would be the negation of saying that this is a subset of A. So if we make this assumption, let A be any set, and let's assume that the empty set is not a subset of A. This assumption implies that we can find an element in this empty set that's not contained in A. And that's what this next sentence is stating. However, that assumption right away is a contradiction, because that assumption implies that there's something in the empty set to begin with. And by definition, the empty set is empty. It has no elements. So this is not even possible. So what that shows is that this assumption that the empty set is not a subset of A leads to a contradiction, meaning that assumption had to have been false. Therefore, the empty set is a subset of A. Okay? That's an important property of the subset, or of the empty set. It's a subset of everything. Moving along. We say that two sets A and B are equal if and only if A is a subset of B and simultaneously B is a subset of A. And in this case, we write A equals B using the usual equals notation. That's really important because this provides us a technique for proving whether two sets are equal to each other. It's a two-part proof. We show that one is a subset of the other and the other is a subset of the first. So here's an example where we're using this. Let's let A equal the set of all real numbers x such that x squared is greater than 0. And then let's also let B be the set of all non-zero real numbers. We want to prove that A is equal to B. Okay? Now, you may look at this right away and just sort of in your mind say, well, they seem pretty clear. It seems pretty clear that these are equal. You know, if x is not a real number, or I'm sorry, if x is a real number and x squared is greater than 0, well, we know that x squared is always positive as long as x is not equal to 0, right? Because in that case, x squared would equal 0. But in all other cases, squaring a real number should give me something positive. And that's what this is describing also. B is a set of all non-zero real numbers, all the real numbers except for 0. So when you talk it out like that, it's easy to see that these are the same set, just described in different notation. But that's not a proof. It's not a proof. Mathematical proof requires much more attention to detail and formality to be considered valid. Even proving something extremely basic, like 1 plus 1 equals 2. A formal mathematical proof doesn't resort to intuition so much. It has to be written in kind of a formal way, using definitions and whatnot. So using our definition of set equality, if I want to show that A is equal to B, I have to show that A is a subset of B, and then I have to also show that B is a subset of A. How do we do that? Well, we pick some element in A, some arbitrary element. I say let X be an element of A. The goal is to show that X is also an element of B. And because X was chosen arbitrarily, that a proof of this type would show that every element of A belongs to B, making A a subset of B. So to that end, let X be an element of A. Then by the way A was defined, we know that it's a real number. Okay. Now, if X is equal to 0, then X squared would equal 0, which would rule out that number from belonging to that set A. So X is not in A if X is equal to 0. What does that imply? Well, that implies that X is non-zero. It's not equal to 0. But that's what B contains by definition. It contains the set of all non-zero real numbers. So that alone is enough to say that X is also in B. This proves that A is a subset of B. We have to go the other direction now. So now I'm going to let Y be an element of B. I'm not using X again because I've already used it up here. Okay? Oh, actually, I can see I messed up my notation here. So let's go ahead and just fudge that a little bit. We're going to let that be an X just because I made a mistake and didn't make all these Y's. And that's okay. We'll be more careful next time. Let's let X be some other element that belongs to B. If X is a real number, which we know that it is because all the elements in B are real numbers, and X is not equal to 0, which again, that's from the definition of B. So it follows that X squared is not equal to 0. Because if it were, then X would have had to equal 0, and we just said that that's not the case. Okay? So if X squared is not equal to 0, then that leaves only two other possibilities. Either X squared is less than 0 or X squared is greater than 0. Because that's the case for any real number. Any real number is either greater than 0, less than 0, or equal to 0. There's no other options. However, we know that when you square a real number, you never get something that's negative. So this case never actually happens. X squared can't be less than 0. So that narrows it down to just this case. X squared must be greater than 0, and that's the defining property that puts X in A. So that shows that B is a subset of A, and there we have a proof that A and B are equal because they're subsets of each other. Okay, that's where we're going to end this video. We'll run through the rest of this in the next video.